Hello everyone, it's Cody from 19. Today is day 78, my challenge day. And from the last video, I started a new project. As you can see, I just following this tutorial. In the last video, I just forked the repository to my local GitHub. And I think it was better to start a new project by using these MV Pro Core library as a third-party library in my project. So I just configured some CMake lists in my new project by just following the same CMake list provided by the MV Pro Core. As you can see, I'm just following the license from the NVIDIA Corporation. Everything is just same, but I just configured new project to start my own project under the Apache license 2.0. So everything works fine, and I'm really excited to start a new project. Instead of just struggling to setting up everything myself. Uh, now I can focus on more the rendering algorithms, unlike focusing on setting up everything and resources like descriptor and creative buffer, how to bind memory in the Vulkan. Now I don't need to do that anymore, thanks to the NV Pro Core. Okay, let's start. So now I'm going to use default host operation extensions and acceleration structure and the rate query extension, which is provided by the Kronos group. Then, okay, let's move on next steps. So as you can see in this tutorial, the tutorial said uh, the bandwidth between the RAM and CPU, or the bandwidth between the VRAM CPU, is really faster than the transferring bandwidth between the RAM and VRAM. So it means that it takes much longer than if we want to transfer data from GPU to CPU. It's really kind of a high cost works than the transferring between the RAM and CPU and VRAM and GPU, because this is a hardware issue. Entirely on the GPU and then only copy image data back to the CPU at the end. Compress data to the GPU and decompress to make transferring the RAM. So in regard to number one guidance, so we can compress a certain data in CPU, like we have we can have a pure image like um, which is not compressed by some of the image format, but as usual we use JPEG or PNG to compress the image size while we don't lose any data in the image. Uh, this is some similar logic that I mentioned here. In regard to number two, we can just minimize the number of transferring between this RAM and VRAM. Like we just transfer once the data to the GPU, and the GPU do everything with the parallel way, and then just GPU send image back to RAM as a result. Then we just need just two transferring in total. So that's the one way to improve this problem. So Vulkan takes a comment buffer approach to improve this problem by recording some GPU commands like vkcmd draw index or like vkcmd trace array, which is the GPU commands in the CPU side, and then we can uh, submit the comment buffer to the graphics queue or the transfer queue, some of the queues that support transferring at once. So, so that we can minimize the number of transferring itself. Guys have their own strengths. Secondary. So for the memory allocation in Vulkan, it's a bit lower level programming than we are used to allocate in the user application. For example, in the malloc function in C or C++, it's more complex than it appears to end user because we're just using them. But in the implementation, they have some of the sub steps to allocate memory, like create a target instance, get a target instance, which is the user want to allocate the memory. And we need to allocate the actual space of memory from the hardware memory. And then we need to bind them, the allocate space to the target provided by the end user. So that finally uh, we can give the memory for the instance. But it's a bit tedious uh, to do these steps for every allocation. So there are some of the allocator implementation in nvvk, which is a dedicated memory allocator, and the DMA memory allocator, and the VMA memory allocator. These two DMA and the VMA is a production level of memory allocator that can be used, but uh, in this tutorial, we are going to use a dedicated memory allocator, which is a really simple implementation. The allocate the memory, single memory for per resources. Also, it has some kind of a limitation because the single memory allocation per resource is limited in the hardware. Source here. Okay. Where thank you for your need to specify what the buffer can be used for, and use the buffer is flag. actually use the buffer as a storage buffer. So buffers in the Vulkan is similar to a pointer type to an array of C++, but the difference is we need to specify a specific buffer usage flags to a certain buffers. And also in the ray tracing extension, we use a buffer to render an image with a storage buffer usage flag. The storage buffer means, which means the program GPU can read and write it, and the storage buffer simply means that for so these two characteristics is these are characteristics of storage buffer Vulkan that I didn't understand in the previous recording. So we want buffer memory to be both host feasible and host coherent. How to create a buffer. So by setting host feasible and host coherent memory requirement flags in the buffer creation, it means that we still can read and write the buffer in CPU, even though the buffer exists in GPU. And also some part of the cache management will be handled automatically. Like creating flow structure, describe how to create an object that has function creates an object. Compute the size buffer and create the buffer as follows. Storage by size. Eight. Render width. The dimension is 3 because we have RGB channel and also size of float for each element. So this is the total device size in our for our storage buffer. So each pixels has a float side, and we have three channels for RGB, red, green, blue, and we need amount of pixels as much as render height multiplied by the render width, which is the resolution of our image. And we can create buffer create info with nvvk buffer create info. Specify size, which is buffer size, and create info usage, storage buffer, and transfer destination means. We pointer of buffer create info struct usage. Let's use multiple line for this. If we need applique memory property device local bit, host visible bit, and host current bit. So we need applique memory cache bit. 30 floating point image, manifold and USB to store. This work has to support transparency in 6 speed floating points. This for speed and various data from GPU to CPU. Okay, it's really good to see the actual memory from the GPU in the CPU side. I just finished the chapter 3 of this tutorial. The next thing is comments, and I will do this in the next recording. Before I'm going to stop recording, let's recap first. So what I did is I learned about the GPU memory, the memory model in the Vulkan API, and how to allocate the memory in Vulkan, uh, about the process, the sub steps of memory allocation in Vulkan, and I've seen how we can simplify that by using memory allocation process by using memory allocator provided by the frameworks. And we've learned about the Vulkan buffers, what is the buffers for, and how to create them, which which flags is required by the storage buffer, and each of the flags means. And lastly, we've seen how to retrieve data from GPU to CPU and actually print them the CPU side by calling the map and reinterpret cast the void data pointer type to the float pointer and then unmap memory again. And after this code, after these statements, we can't access this memory anymore. I think let's test that. It seems okay, but I think this is an old memory. This is a coherent memory between the GPU and CPU, but at this point, this is a outdated memory because we unmapped memory from the CPU, and there can be some updates on the GPU side. So this is all for today's recording, and as always, thanks for watching. See you next video.